What we're going to look at now is Nuclide notation. How do we describe what's in the element? Right, first we have a symbol for an element, which will be a letter or two letters. And then we put a superscript, which is letter A and Z underneath. So A at the top, Z at the bottom. What do these letters mean? Well, A is the atomic mass, which is basically the sum of the protons and the neutrons that are in the nucleus. Z is the atomic number, which is the number of protons. Now you should remember that the number of protons will basically tell you which element it is. If it has a different number of protons, it will be a different element. The numbers of neutrons can be different though. Which brings us on to an isotope. This is when you have the same element with differing numbers of neutrons. Remember, the proton number gives you the element, but you can have a slight variation in the number of neutrons for it to be still the same element. For example, this is the chemical symbol for carbon. Notice that the atomic number is 6. It has 6 protons. It has 12 nucleons, which means that 6 plus 6 adds up to 12. So this isotope has 6 protons and 6 neutrons, and it's called carbon-12. On the other hand, we could have another element which is basically the same element. It's got 6 here, this is the atomic number, so it has 6 protons. But it has 14 nucleons, which means it has 6 protons and 8 neutrons. This makes it a different isotope. It's the same element because it has the same atomic number, in other words, the same number of protons. But it's an isotope. Now, to look at the different kinds of nuclear radiation, we have alpha, beta, and gamma. We know that alpha doesn't get very far. A piece of paper will stop it. A centimeter or 2 of air will stop it. B will pass through paper, but it will not go through a reasonably thick piece of aluminium. Gamma, however, will go through thick aluminium and will also go through some lead, but a thick piece of lead will stop it. Now, this is all nuclear radiation. These come from the nucleus. Now we're going to look at the ionizing strengths of alpha, beta, and gamma. Alpha particles are highly ionizing. The energy is absorbed very quickly, and therefore it doesn't penetrate very far. Beta particles also ionizing, but the energy is absorbed quite quickly, but not as quickly as alpha particles. Therefore it penetrates a little bit more because it's able to go further into the substance. Gamma rays are not very ionizing, so they're able to travel some considerable distance before their energy is absorbed, and therefore that it penetrates quite easily. Other properties of alpha, beta, and gamma radiation. Alpha particles are particles. They're fast-moving helium nuclei, and they come from the nucleus of the atom. It's a heavy particle. It's made of 2 protons and 2 neutrons, so it has a positive charge of +2. Beta particles are fast-moving electrons. They're small, and they have a charge of -1 because it's the same as an electron. Gamma rays, notice that these are not particles, these are rays. This is also radiation that comes from the nucleus. It's part of the electromagnetic spectrum, so it has no charge, it has no mass, and it is not a particle. It's part of the electromagnetic spectrum. More details of alpha decay. Now, what happens is that if a nucleus is unstable, a little piece comes off it, and this will be, let's say, an alpha particle. So it means that that nucleus will become lighter by 1 alpha particle. So therefore, since an alpha particle has 2 protons and 2 neutrons, it will lose 2 protons and 2 neutrons. The atomic number reduces by 2 because it loses 2 protons. The atomic mass will reduce by 4 because it releases 2 protons and 2 neutrons, so it becomes 4 nucleons lighter. An example in an algebraic way was that this is the element X, whatever that is. The atomic number is Z. The atomic mass is A. The alpha particle, remember, has 2 protons and 2 neutrons, so the atomic number is 2. The nucleon number, or the atomic mass, is 4. And what's going to happen is that A loses 4, so we're going to be left with A minus 4. And Z loses 2, so we're going to be left with Z minus 2. So this is element X, so this is A minus 4, and this is Z minus 2. However, we've written X here. This is a mistake, because notice that Z defines the element, and since the element has changed, this must be another element, so it can't be X, it must be something else. Let's call it Y. Let's look at an example. Thorium has a proton number of 90, an atomic number of 90. It has an atomic mass of 232. Now, it loses another particle, which means that it loses 2 protons and 4 nucleons. So 4 and 2. What's going to happen to this value here? Well, 90 is going to be reduced by 2, so this will become 88. 232 will be reduced by 4, so that will be 228. And of course it's not going to be thorium anymore because it's a new element. It's now got 88 here. So it actually turns into radium. Beta decay. Beta decay is when a beta particle is emitted from the nucleus. A beta particle is a fast-moving electron. But the problem is this. There are no electrons in the nucleus. So how is it possible that a beta particle, which is an electron, comes from a nucleus? We know that neutrons and protons are in the nucleus, and what happens? A neutron decays into a proton and an electron. So you basically start with a neutron, it turns into a proton and an electron. So there we go. Neutron turns into a proton plus an electron plus a very small particle called an antineutrino, which is kind of paired with the electron. So what happens here is that we have X releases B, which is a beta particle, so and it produces a new substance X. We know that Z was before, it now has an extra proton because one of the neutrons has turned into a proton, so Z goes up by 1. However, A, it did have a certain number of neutrons and a certain number of protons. One of its neutrons has turned into a proton, so the total is going to be the same. So this will be A, and this will be Z plus 1. And of course, this will not be X anymore because it's a new element. We'll call it Y. Sometimes we write the numbers on a beta particle here. -1, this gives effectively the charge of that particle, and 0 gives the effective mass of that particle, which is almost 0. Notice that the atomic mass is unchanged. The beta particle doesn't take any mass away. A neutron turns into a proton, so the total mass is the same. Here we have an example. Actinium releases a beta particle, which is 0 minus 1. What will it produce? Well, first of all, what will happen to the atomic number? Well, this will basically, one neutron will turn it into a proton, so this will increase by 1, so this will be 89 plus 1, which will be 90, and 228 will be the same because there's no change in the mass. So it'll be 228 and 90. We don't have actinium anymore, we have a new element which is thorium.